Okay, so just imagine for a second, a computer that could solve problems we currently think are literally impossible. And not just by being a little bit faster, but by working in a completely different way, in a totally different reality. Today, we're diving headfirst into the world of quantum computing. We're talking about a technology that's poised to change, well, pretty much everything, and the incredible, high-stakes race to actually build it.
For decades, our entire world has been built on a very simple language, ones and zeros. It's the language of classical computers, and it's been incredibly reliable. But here's the thing. The biggest challenges we face, things like climate change or discovering new medicines, they're just beyond the reach of these machines. We are right on the edge of a new era, a new kind of computation that promises to unlock all those solutions.
So let's just ask that question one more time. What if you could design the perfect molecule to pull carbon right out of the atmosphere? Or create a new drug that's tailored specifically to your DNA? I know, it sounds like science fiction, but this is the real core promise of quantum computing, and it could absolutely revolutionize everything from medicine to finance.
So what does this actually mean for us in the real world? Well, we are talking about simulating molecules to discover life-saving drugs in a fraction of the time it takes now. It could mean untangling the mess of global supply chains to make them perfectly efficient, or creating communication networks that are, by the laws of physics, impossible to hack. It's really a tool for modeling the world's most complex systems with an accuracy we can barely even wrap our heads around today.
All right, so how on earth is any of this even possible? Well, the secret lies in a tiny but unbelievably powerful building block from the quantum world. To really get it, we have to understand the huge leap from the classical bit to its quantum cousin, the qubit.
So, the phone in your hand or the laptop on your desk, they use bits. And a bit is super simple, right? It's like a light switch. It's either on or it's off, a 1 or a 0. That's it. But a quantum bit, a qubit, is a whole different ballgame. It's more like a dimmer switch. It can be a 1, it can be a 0, or, and this is the mind-bending part, it can be a blend of both at the exact same time. This amazing ability is called superposition, and it's the secret sauce. It's where all the power comes from. Just look at the scaling here. You add one classical bit, you get one more operation. But you add one single qubit, and you double the computer's potential power. It's an absolute exponential explosion of processing capability.
Here's a great way to think about it. Imagine you have a giant, complex maze. A classical computer would have to try every single path, one after another, until it finally finds the exit. It might be fast, but it's still just brute force. A quantum computer, on the other hand, thanks to that superposition trick, can basically explore every possible path at once. It sees the entire map of possibilities simultaneously. That is the quantum advantage.
So, if qubits are the magic ingredient for this new age of computing, the next question is obvious. How do you actually build one? Well, that simple question has kicked off this fierce global race between tech giants, tiny startups, and entire countries, all trying to be the first to engineer a stable, scalable quantum computer.
And as you can see here, there's more than one way to cook a qubit. Each of these approaches has its own pros and cons. Superconducting qubits are kind of the most mature technology, but they're really noisy and they lose their quantum state super fast. Scientists call that low coherence time. On the other hand, trapped ions have the best fidelity, which means they're incredibly accurate, but they're slow and really hard to scale up. The point is, right now, there is no clear winner, which makes this race so incredibly exciting to watch.
You'll often hear companies making big announcements about having more and more qubits. But honestly, that number can be really misleading. The single biggest challenge in this entire field isn't about the quantity of qubits, it's all about their quality. These things are unbelievably fragile.
Now, this is just wild. It's the estimated number of today's noisy, error-prone physical qubits that you need to create just one stable, usable logical qubit after you do all the error correction. Let that sink in. That's like needing 1,000 light bulbs, or maybe 10,000, just to get one that you can rely on to work properly. The engineering overhead is just immense.
And this really lays out the mountain that researchers are trying to climb. The tiniest vibration, a stray magnetic field, even a tiny shift in temperature can completely corrupt a qubit and wreck a calculation. So building systems to shield them, to correct for all their errors, and then to scale them up to the thousands or millions needed, it's truly one of the hardest engineering problems humanity has ever tried to tackle. But even with these huge challenges, The potential reward is so enormous that it's fueling what you can only call a quantum gold rush. The promise of this tech is attracting billions and billions of dollars in investment from governments and private companies alike.
So, in 2024, the quantum market is already worth almost $1 billion, which is a really solid starting point. But honestly, that's just the launch pad. By 2035, that market is projected to absolutely skyrocket to over $17 billion. We're talking about a compound annual growth rate of 32%. That kind of number shows you just how confident investors are that these massive engineering hurdles will eventually be solved.
And here's what's really interesting. The fastest growing slice of this market isn't actually selling the multi-million-dollar machines themselves. It's what's called Quantum as a Service, or QaaS. Basically, it means companies can tap into quantum power through the cloud so they don't have to build a giant super-cold lab. And this model is projected to grow at an incredible 57% per year.
So this gives us a quick snapshot of who the leaders in the hardware race are right now. You've got companies like IonQ and Inflection who specialize in different qubit technologies sitting at the top. But look at how big that other slice is. It tells you the market is still really fragmented. There is a huge amount of competition and innovation happening all across the board.
So, what we have here is this incredible, world-changing promise on one side, and these massive, fundamental challenges on the other. And that brings us to a really crucial question about the future of this whole industry.
Is this technology actually going to deliver the breakthrough revolution that everyone has been promising? Or what happens if progress stalls? Could the industry face what they call a quantum winter? A period where a failure to show real practical results causes all the funding and interest to just dry up?
This quote really gets to the heart of it. That acronym NISQ, it stands for Noisy Intermediate Scale Quantum. That's basically the kind of machines we have today. The pressure is on for these current generation systems to prove they can deliver real, actual business value, and soon. Because if they can't, the river of investment that fuels all this amazing research could slow to a trickle.
So I think the key thing to take away here is this. For all the incredible promise, for all the mind-bending science, this future of unimaginable computing power, it's not a given. It's not just going to happen on its own. It has to be engineered and tested and scaled up one painful qubit at a time. This future is being built right now as we speak by thousands of brilliant people literally racing against the fundamental limits of physics. And you know what? Whether they succeed or not isn't just some academic victory. It's going to define the next era of technology for all of us.